From News to Music, and the next talk is given to you by Minju Park, and it is about exploiting negative preferences in content-based music recommendation with contrastive learning.
Okay. Hi everyone, I'm glad to meet you. I'm Minju Park from Music and Audio Research Group, Seoul National University. The work I'll be presenting is about exploiting negative preference in content-based music recommendation with contrastive learning. So firstly, I'd like to introduce the motivation of this study. The naive motivation was very simple at first. For personalized music recommendation, we have to understand or explain the user's music taste. And then I came up with a question, which is easier to explain, musics I like or musics I don't like? Just simply thinking about it based on my experience, my answer was that it is easier to explain musics I don't like. So throughout this study, we focus on this hypothesis and we'll be finding some evidence in it. These are the two research questions that I want to show through this study. First, I want to find out what characteristics negative preferences have in terms of explaining music taste. And according to our hypothesis, that it is easier to explain the songs I don't like, negative preference in music taste has to have more distinct characteristics compared to the positive, and we'll see what happens. And secondly, I also want to see how applying negative preference will help improve music recommendations. So we'll be discussing the advantages of exploiting negative preference in music recommendations. Let's take a look at the existing studies. As a lot of you know, there are collaborative filtering and content-based methods in recommendation algorithms. And collaborative filtering can involve one's music taste in the latent space, but when it comes to explaining the music taste, the content itself has to be considered. So we'll be using the content-based method as the main framework of our study, of our model. But however, there's also a drawback that the content-based methods highly rely on similarities. So in our work, we'll be exploiting the user preference data along with the contents. We also want to focus on recommendation systems applying negative preference. There are existing works applying negative preference in recommendation systems, and in case of music recommendation, applying skipping behaviors might be an example. However, most of these studies conclude by proposing a novel architecture with increased performance, and improving the model's performance is important, but the fundamental analysis of why better recommendations have become possible is sometimes overlooked due to the focus on the engineering perspective. Therefore, in our study, we would like to focus on illuminating the specific roles of negative preferences compared to the positive preference. Now let's talk about our methodology for answering the research questions that we set up in advance. This is the overview of our model framework. And since we are on content-based music recommendation, we extract the features of the songs first. In order to focus on the identity of the music content itself, we adopted pre-trained models based on self-supervised manner to ease out our training procedure. We'll be using these three different feature extractors to evaluate the stability of our proposed method. Then we feed the extracted features in the contrastive learning stage. We differently condition positive and negative preference here in order to compare the final recommendation results. And in fact, this is the main part of our model, since the main goal of our study is to understand the effects of negative preference through the comparison of recommendation models in which preferences are differently conditioned. I'll explain in more detail how we applied preferences differently. So we designed the contrastive learning models with three different training strategies, exploiting preferences of both positive and negative, positive only, and negative only. For convenience, I'll be calling them CLEP-PN, CLEP-P, CLEP-N, respectively. As it is seen in the contrastive loss formula, contrastive learning is basically trained to embed data pairs with the same label close together and embed the data pairs with different labels far away. And in our case, we will be conditioning the way we label the data pairs according to the three models. For CLEP-PN, which exploits positive and negative preference, positive pairs and negative pairs are considered as the same label, so that the model will embed these pairs of songs close together and embed the positive-negative pairs of songs far away. And for clap P, we're going to consider the positive-positive pairs as the same label, and vice versa for clap N. And in fact, this is the model we would really like to focus on, since this is the one exploiting negative preference. So if we think of a user's music taste as a complex distribution of songs the user likes and dislikes, we were interested in which of these three models most similarly simulates the distribution. And lastly, with the embedding after the contrastive learning, MLP layers are added and trained to match the ground truth of whether the user likes or dislikes the song. So with this framework, we did the experiments, and to train and evaluate our model, we needed a personalized user preference data set. So we conducted a web-based survey asking participants about their music preference. We recruited 24 volunteers, and they were asked to listen to about 200 music clips and answer whether they liked or disliked each song. So we were able to obtain 24 individual personalized music preference data set and 200 preference data per person. So we divided them into a training set and a test set, then trained the models with the training set and assessed their performance on the test set. For the evaluation, we chose accuracy, precision, recall, AUROC, and false positive rate as our evaluation metrics. These are like common metrics used in classification tests, but in our case, precision and false positive rate were considered somewhat special. What these two have in common is that false positives are involved. Then what's so special about this false positive is that false positives have more significance in recommendation tasks than in general classification. Like for instance, when it comes to music recommendation, false positives indicate the recommended songs which the user dislike, while the false negatives indicate the not recommended songs which the user like. So from the user's point of view, false negatives are almost impossible to recognize. On the other hand, false positives will definitely have a negative effect on the user experience. So like this, false positives are a clear concern in recommendations, and there are several studies conducted supporting this. So precision and false positive rate will help analyze the practical utility of a music recommendation system. Now the conclusion part. We evaluated our models by having our trained models predict the user's preference for every test set of our individual preference data set. The experimental results were analyzed through the Friedman test. Among the 5 evaluation metrics, accuracy, recall, and false positive rate showed statistically significant differences in models regardless of the music feature extractors. And in order to verify specified relationship between the models for these 3 evaluation metrics, Wilcoxon-Sign rank tests were performed as the post-hoc analysis. So if you see this, although the relationship between clap PN and clap P was slightly different depending on the musical feature extractors, but the clap N, which was the model we want to focus on, outperformed the other 2 for accuracy and false positive rate, while showed the lowest recall among the 3. So to sum up these results, focusing on the clap N showed the best accuracy, the best false positive rate, but the poorest recall. False positive rate is sometimes called an anti-metric for recall, which is a metric aware of the irrelevant items returned by the recommendations. And previous studies say that when distinguishing recommendation systems with similar relevance, anti-metrics are more valuable than classical metrics. So considering this point, we would like to insist that the fact clap N is showing a high false positive rate is still a strong evidence of its potential to be utilized in recommendation system despite this poor recall. So based on these results, let's get back to the research questions we wanted to answer. So for the first question, since we have shown that clap N had the highest accuracy, we can say that clap N simulates the true distribution of music taste most similarly among the 3. These are the examples of the embedding space of the trained model based on one of the participants. You're able to see that the embedding part was done well as we designed, and the fact that clap N showed the highest accuracy suggests that our music taste has a similar distribution to the picture on the right. This tells that songs with negative preference have more distinct characteristics. And the fun part is that it is also supported by the concept of serendipity, which is a measure indicating the unexpectedness of a recommendation. The fact that users react to unexpectedly good things points out that there is a chance of finding songs the user may like in an unpredictable area of the user's music taste, which is explained by our study. And for the second question, according to our experimental results, CLEP-N tended to have low false positive rate and high precision. And since false positives play an important role in terms of user experience, the finding that exploiting negative preference contributes to improvement in false positive metrics can tell that exploiting negative preference will be expected to make significant progress in music recommendations. So to summarize, throughout this study, we analyzed the role of negative preference in users' music taste by comparing 3 models which differently condition contrastive learning exploiting preference, as we call it CLEP-PN, CLEP-P, and CLEP-N. And by identifying the advantages of CLEP-N, we provided evidence for the possibility of utilizing negative preference for music recommendations. And this is it for my presentation, and if you have questions, feel free to ask. Yeah. Thank you.
Thank you. We do have a number of questions, and many of them are concerned with eliciting the negative feedback. In your study, you of course elicited explicit feedback from people saying whether they not liked songs. But how would this work in practice? How would you elicit the negative feedback?
In practice, like getting explicit negative preference is still a hard problem, I guess. But the thing I wanted to tell you is that the focus of this study is like to understand the effects of negative preference in music recommendations. So for the real world application, we have lots of things to do. And I think I have to think about it.
Okay, thank you very much. Now, the second question is focusing on the model you built. For the study, you only used 24 users.
Yep.
So how do you see problems of overfitting in that? Do you think that was a specific set of users that you just tailored the preferences to?
In fact, the model was trained like individually for one person. So we didn't use the whole 24 data set in the whole training. So we specialized the training for per person. So like it wasn't, I don't think there was an overfitting because the lack of data, but the results show that statistically significant differences. So I think that would work for it.
Okay, thank you very much. Another concern that was raised is how about temporal patterns in preferences, both positive and negative? Your preferences might change with seasons or with the context.
There are like lots of things to concern in music recommendations, but like for example, like context and things. But like, as I told you, like the main focus that I wanted to see was that comparing, like exploiting positive preference and negative preference, like make the different results. That was the main point I wanted to see. So like considering other contexts will be another problem that we can do in the future work.
Okay, then one final question. What do you think about the generalization of your population that you studied, these 24 people, to other people in the general population? Do you think there was some bias in the people you studied?
The participants for collecting the data set were recruited probably much randomly. So I think it will make sense if we like expand the population. I think it will have a similar result, but I want to try on that.
Okay, great. There are a lot more questions, so please answer them later on in the platform. Let's thank the speaker again.